Welcome to everyone joining us for the AI Solutions FreeFlyer Multi-Objective Optimization webinar today. We greatly appreciate you all taking the time out of your day to join us from wherever you are on the planet. I am Regis Ghani, AI Solutions Space Product Account Executive, and one of your moderators for today. I am joined by Danny Brown, also a Space Product Account Executive, and he will be monitoring the Q&A for the webinar. So before we begin, let's go over some logistics for today. All attendees are muted and cameras will be off for the duration of the webinar. We'll be recording the webinar for future reference and playback on YouTube. We'll follow up with slides after the webinar. You may use the Q&A function or the chat function to pose any questions during the webinar, and Danny will interject when appropriate or at the end of the webinar, go over the questions. And additionally, you may use the chat function to ask any questions for us. And now for our presenter, Luke Schoenwetter graduated from the University of Alabama with both a bachelor's and master's in aerospace engineering. During his time in Alabama, he was a research assistant for the Astrodynamic and Space Research Lab. His area of research included orbital mechanics, trajectory optimization, and differential games. After graduating, Luke began working here at AI Solutions as a software engineer. He now works on the FreeFlyer development team and focuses primarily on trajectory optimization and numerical solution methods. Welcome, Luke, and take it away.
Thank you, Regis, and welcome everybody to this FreeFlyer webinar, where we are excited to share with you some of the new features coming in FreeFlyer 7.10. Way back in FreeFlyer version 7.6, we added our generic optimization functionalities. And then in FreeFlyer 7.8, we built on those with optimal control features. And now in FreeFlyer 7.10, we'll be adding multi-objective optimization, which is going to be the topic of discussion for today. So first, we'll discuss what multi-objective optimization is, what that means. And then we'll discuss some of the methods behind the capabilities that we're adding in version 7.10. And we will also look at a couple sample problems and their solutions. So first off, what is a multi-objective optimization? In order to understand the topic, I'll start by posing an astrodynamics problem, and then we'll discuss how we can use multi-objective optimization to solve that problem. So let's consider a problem where we're starting from Earth and we want to visit 3 asteroids. And those 3 asteroids are going to be chosen from a cloud of 22 asteroids. We're going to stay 90 days at each asteroid. And to get from each point in our asteroid tour to the next point, we'll use 3 burns. We use a departure burn, a mid-course burn, and an arrival burn. And of course, at the end of that tour, we're going to end up with a total amount of transit time and a total amount of delta V expended, and we're going to want to minimize those 2 things. So here's our cloud of 22 asteroids. And again, we're going to start at Earth and we're going to transfer to one of these asteroids and then transfer to 2 other asteroids in sequence. So we need to transform this problem into a language that the computer can understand. Numbers. So we'll consider each one of these asteroid choices to be a variable in the problem. So we want to choose 3 asteroids. Let's say we'll choose 2, 16, and 5. That means that we're going to start at Earth. We're going to transfer to asteroid number 2, and then to asteroid 16, and then to asteroid 5, all in sequence. And then at the end of that transfer, again, we're going to end up with 2 objectives, and we want to minimize those objectives. And the goal of multi-objective optimization is to come up with a set of trade-off solutions, in technical terms called a Pareto front. So the Pareto front is the set of trade-offs that you as the engineer can choose, the set of optimal trade-offs. And then there will be another set of solutions represented by the gray dots in this diagram that are considered dominated by the Pareto front. In other words, those solutions don't have objective values that are better in any of the categories so specifically transit time and delta V for this example, than any of the solutions in the Pareto front. So we have our asteroid choice variables, and we have delta V and transit time objectives. And we need some function that is going to transform the asteroid choice variables into those objective values. The way that we're going to do this is we're actually going to use a subsidiary local optimizer to solve the transfer leg problem for each iteration of the multi-objective optimizer. And that's going to look something like this animation that we have on screen right here, where we have a start point and we have an end point, and those are either Earth or an asteroid, and another asteroid is the end point. And so we will solve the transfer leg between those 2 points for minimum delta V, and then we will solve the next transfer leg and the next transfer leg. And at the end of that sequence, we'll have our 2 objectives that we can then feed to the multi-objective optimizer. So we have a couple sequences of asteroid choices here. And each one of these sequences is going to be fed into our user function, which is then going to output the objectives for the multi-objective optimizer. Now, something that we can notice right away is that we have Pareto front domination going on in this set. Specifically, solution number 2 here in the list dominates solution number 4 because both of the objectives are better. Specifically, we have a lower delta V and we have a lower transit time. So there's no reason for us to choose solution number 4 over solution number 2, because all of the objectives are worse. And going back to our Pareto front diagram, this dominating solution number 2 corresponds to a point in the Pareto front, whereas the dominated solution number 4 corresponds to one of these gray points. So now we'll change gears and we'll discuss something called genetic operations. And genetic operations are going to allow us to take our current set of solutions and construct another set of solutions for evaluation that's hopefully going to move us closer to better solutions and advance the Pareto front in a positive direction. And how we'll go about this is we will look for solutions in our current population that have desirable values for our objectives. So in this particular example, we would look for solution number 1, which has the best objective value for transit time, and the last solution in the set, which has the best objective for delta V. So we'll isolate these solutions and we will recombine them. In other words, we will take most of this first transfer sequence, and then we'll take a small portion of the second transfer sequence, and we'll put them together. And the hope is that the new recombined genome that we've created retains the positive elements of both solutions and gets rid of the non-desirable traits from both of them as well. Now, this doesn't happen all the time, doesn't even happen most of the time. But because we have the power of the modern CPU at our fingertips, we can do this operation over and over and over again very quickly. And as we do that, eventually we will come across instances where this does actually hold true, where we recombine a new genome and we retain some of those positive traits from both of them. And as that process goes on and on and on, our solutions get better and better, and the Pareto front gets more and more concentrated towards the optimal set of trade-offs. So we use our current population, feed it into the genetic operation, and we get out an offspring generation. And that is the genetic algorithm in a nutshell. So to recap, we first compute the objectives for all members of our population using that user function. And then we will evaluate the expansion of the Pareto front based on the objectives that we get back. And finally, we'll generate a new population using genetic operations. And then the cycle repeats to infinity until we as the user decide to halt it. So now we'll begin looking at some of the solutions for this asteroid tour problem. So when we feed this problem to the multi-objective optimizer, we let it run until some stopping condition. These are the solutions that we get back. On the right, we have a plot of the Pareto front in 2D space, and on the left, we have a table of all of our solutions that is sorted according to the total delta V objective. So the solutions here at the top of the table have the least delta V, and the solutions at the bottom have the most. Now, something that is interesting to note about this Pareto front is that it doesn't look like a front like we saw in that diagram previously. And there is a particular reason for that. So backtracking just a few minutes to when we were talking about genetic operations and how we select solutions from the population to be included in the reproduction of the next population. We looked at transit time and delta V, and we want to find solutions that have desirable objective values for those two categories, and then we select those solutions for reproduction. Now, at the end of the day, the solutions we care about are total delta V and total transit time, but I've actually included other subsidiary objectives in this problem to aid in the advancement of the Pareto front. And those objectives are going to be the specific individual delta V's for each transfer leg. So this first delta V sub 1 objective is going to correspond to the delta V needed to get from Earth to asteroid 5 in this first element in the list. And then delta V sub 2 is going to correspond to the delta V needed to get from asteroid 5 to 8, and so on for 8 to 15 for this delta V sub 3 objective. Now, again, all we really care about at the end of the day is total delta V and total transit time. But when it comes to the multi-objective optimizer figuring out new ways to advance the Pareto front, it may be beneficial to look at some of these other sub-objectives. Specifically, solution number 4 in the list here, like we said before, is dominated by solution number 2 for our total delta V and transit time objectives. But when we include these other objectives, we see that solution 4 and solution 3 actually have very desirable traits in some of these other categories. And so although total delta V and total transit time aren't traits that we want to retain through recombination, delta V sub 1 and delta V sub 2 are. And so we'll also include some of these other solutions in the generation of the next population, the offspring generation. And in so doing, we will enhance the advancement of the Pareto front, and we'll get better solutions faster. So that is why the plot on the right here looks the way it does, and it's not a smooth front. It's because we're looking at the Pareto front in only 2 dimensions, when in reality, we're including total delta V and total transit time along with these other 3 individual delta V objectives. So we'll examine the solution down here circled in red, which corresponds to this top solution in the table, the best solution in terms of total delta V. So we're going to go from asteroid 9 to asteroid 20 to asteroid 18, and we'll look at what that looks like in this animation here. Again, the sequence is up here in the top right. So asteroid 9 to asteroid 20 to asteroid 18. You can see we've just arrived at asteroid 9. Again, there's going to be 3 burns per transfer leg. So departure, mid-course, and arrival for each leg. So departure, mid-course, and arrival for the first leg, and then so on for the second leg. And we're watching the last leg play out right here. So this is what the quote-unquote most optimal solution, the extreme solution, looks like for total delta V. but you as the engineer are able to look at the data that the multi-objective optimizer comes up with and make a decision based on all of the trade-offs that are available to you. Whereas in a single objective optimizer, obviously you're only looking at one objective, and you can use that single objective in creative ways and come up with interesting ways to combine all of these objectives into one value. But multi-objective optimization has the advantage of allowing you to examine the entire front of trade-offs and make a decision based on that information. So now we'll look at a second example problem of how you can use these features. This one is going to involve scheduling passes of ground stations for a constellation of spacecraft. So let's say we have 50 spacecraft in low Earth orbit constellation. We have 3 ground stations to access, and we want to schedule one pass for each of our spacecraft. Say it's one downlink over a 2-day period. So we need one contact event for each spacecraft over 2 days. And our goals for this scenario are going to be to maximize the average duration of the pass for each spacecraft across the entire constellation. We also want to maximize the shortest pass duration when we take into account all of the scheduled passes. What is the shortest amount of time that we have for any given spacecraft? We want to make that value as high as we possibly can. And then we also want to maximize the number of passes scheduled in darkness. So we want to not schedule the passes during the daytime if possible. So the first step in solving this problem is going to be simulating and logging the data that isn't going to change in between multi-objective optimizer iterations. And that non-changing or static data is going to be the potential contact windows. And then from those potential contact windows, the multi-objective optimizer will choose specific available opportunities to use as the actual scheduled events. So each time one of these spacecraft in the constellation flies over a ground station and comes into comms range, it lights up green, and that corresponds to an event that's being logged or sent to a file for later retrieval. And in that way, we don't have to re-simulate all of this and use up all of that computational time at each iteration of the multi-objective optimizer. We can just retrieve the data that we've already simulated. So this is what that data ends up looking like after we've performed that simulation. So along the y-axis, we have all of the different spacecraft. On the x-axis is time, and we're not looking at the full 2 days here. We're only looking at 12 hours, just to make things easier to look at. Spreads the boxes out and makes them easier to see. But really, this data is 2 days long. And in green, we have all of the desirable contact opportunities, the ones that happen in darkness. And in red, we have the contact opportunities that we can use, but we don't necessarily want to use because they are during the daytime. And now we'll talk about how we transform this problem into a language that the multi-objective optimizer can understand. So what we're going to do is we're going to have a variable that corresponds to each one of these spacecraft. Again, we want to schedule one pass per spacecraft. Now, each spacecraft is going to have a list of potential contact opportunities that we can use. So let's take, for example, spacecraft 27. Spacecraft 27 is going to have 4 potential contact opportunities, assuming this shortened segment of data that we're using. That's not the full segment of data again, but so 4 contact opportunities. And that means that x sub 27 over here in our contact windows choices vector is going to have a value of either 0, 1, 2, or 3. And based on the value of x sub 27 chosen by the multi-objective optimizer, one of these 4 contact opportunities will become the scheduled pass for spacecraft 27. And we'll perform that operation for all of these spacecraft, corresponding to all of these contact window choice variables. And once we do that, we will have a complete schedule with 1 pass for every spacecraft. This is the same data viewed in a different way. Now we're looking at colors that correspond to the different ground stations. So we have 3 ground stations. Red is going to correspond to the first ground station, blue to the second, and green to the third. Something that we'll notice by examining this plot is that in certain locations, such as over here on the left, there are places where 2 different spacecraft are flying over, coming into comms range of the same ground station at the same time. And of course, we don't want to schedule both of those passes because then we're overtasking that singular ground station. And so we have these 3 maximizing objectives that we discussed previously. We're also going to add a minimizing objective. And this minimizing objective is going to be a summation of all of the conflicts, all of the conflicting passes that end up getting scheduled for a particular solution. So let's say that for a particular solution, spacecraft 17 and spacecraft 27 end up being scheduled for these 2 passes right here in the white box. That would end up incurring a penalty that gets fed to this conflicts objective. And at the end of the multi-objective optimizer running, doing its thing, we can then look at all of the solutions and filter out any solutions that have a conflict objective that is greater than 0, or that is scheduling conflicting passes. And in that way, once we get to the end of multi-objective optimization and begin looking at the potential solutions we have to choose from, we can immediately weed out all of the solutions that are, non-physical or that don't meet the constraints that we placed on the problem, specifically that we don't want to schedule conflicting passes. So now we've solved the problem. This is the Pareto front that we get back. You can see it's a nice smooth decreasing function going from right to left in terms of both minimum contact duration and average contact duration. So in other words, as we schedule more contacts in darkness, which is again something that is desirable, something we want to do, we have to give up something in terms of average contact duration and minimum contact duration. So there does exist a solution down here circled in green where all of the contacts are scheduled in darkness, but that solution has a much shorter minimum contact duration than, say, if we move back just a few solutions to here, where we're only scheduling 48 of our passes in darkness. And again, this is the real strength of multi-objective optimization of this feature, is it allows you to come up with all the trade-offs and then visualize them in order to come up with a, you figure out what solution works best for you in your use case. And that's something that can be done manually or something that can be done in a more automated way. So let's say that you have hard constraints on your problem that none of my contact durations can last less than 3 minutes. Let's say that's a hard constraint for me. I can programmatically, without a human in the loop, run the multi-objective optimizer, solve this problem, get this trade-off front, the Pareto front, and tell the multi-objective optimizer to get rid of all of the solutions that have a minimum contact duration that's less than 3 minutes. And of course, that's going to shave off these solutions down here on the far right side with 49 and 50 contacts being scheduled in darkness. And you're left with all of these solutions up here, at which point it's very easy to programmatically tell a computer, lop off the first solution that meets all of these constraints, which is going to be this one. So that's a way to do that operation in a programmatic manner. But it's also possible to do this process in a more manual way if, say, maybe your constraints aren't hard constraints. I don't have like a hard cutoff at 3 minutes. I just want to see what all of my possibilities are before I make an informed decision using all of this data. I can do that using the multi-objective optimizer. I run it, I plot the data for myself like we're doing here, and I can see how much I have to give up in terms of minimum contact duration for each additional pass that I schedule in darkness. So this is the solution that corresponds to 48 contacts scheduled in darkness, and it's a little hard to look at because now we're looking at the full 2 days of data rather than just 12 hours. So the data is it's hard to see, but we have in bright green, we have all of the passes that have been scheduled in darkness, and in red, bright red, we have 2 passes that have been scheduled during the daytime. So one right here and one over here. And then we'll flip to the solution where all of the contacts are scheduled at night, and that's what this looks like. And you'll note that most of the solutions, as I'm kind of like flipping back and forth between the 2 solutions, are staying the same. Very few of them actually move. And that's due to those genetic operations that we were talking about previously. As the multi-objective optimizer runs and produces more solutions, it kind of narrows in on where the best solutions are at in terms of state space, or what the variables in the problem are going to look like. So specifically for this problem, where the contact passes lie. And you'll only see slight differences most of the time for solutions that are close to each other in the Pareto front, like 48 and 50 are here. So again, the big advantage of using this feature over like a single objective optimizer, which we already have in FreeFlyer, is the ability to look at this Pareto front, the trade-off front, and make an informed decision based on all of the potential options that are available to you. So that's all of the material that we have today. In terms of final remarks and recapping, this is a new way to do trade study analyses in FreeFlyer that previously wasn't there. And specifically in terms of discrete state spaces, or when you have a problem that doesn't use continuous variables, such as the asteroid tour problem and the scheduling problem that we looked at. This is a robust way of handling those problems that previously you didn't have access to in FreeFlyer. So those are the big highlights for this feature. And that's all I have. I'll hand things back to Danny and Regis.
Perfect. Thanks so much, Luke. That was very, very informative. Now we will take some questions from the chat and ones that were submitted. Got one here for you, Luke, that says, can I filter out solutions? For example, can I get rid of all the solutions with any passes shorter than 2 minutes?
Yes, so you can. You can do that operation for any of your objectives using any values that you would like to provide as the limit for where you want that filter to apply. So if I have an objective and I don't want to view any solutions that have a value that's worse than X for that objective, that's a feature that is included in FreeFlyer multi-objective optimization.
Perfect, thank you. Next, does FreeFlyer have any features to let me sort through the solutions that are generated?
Yeah, so that goes back to when we were discussing programmatic ways to comb through solutions versus manual ways. If you have hard constraints, or if you have one objective that you know for certain is more important to you than the other objectives, you can use sorting functionalities to sort the Pareto front according to one objective first, and then according to another objective second, and so on and so on for the objectives as you have, in order to create a list that has your preferred or most desired solution at the very top of it.
Fantastic. Thank you, sir.
Mhm.
Let's see here. We've got another one. It says, is there any limit to the number of objectives I can model?
No, there's not. Well, maybe in terms of how powerful your processor is, but that's all.
Okay. Got a couple more here. Does the multi-objective optimizer use the NSGA algorithm?
So FreeFlyer multi-objective optimization gives you access to two different genetic algorithms. One of them is an NSGA derivative, and the other is a SPEA derivative. That stands for Strength Pareto Evolutionary Algorithm. So those are the two algorithms that you have access to.
Fantastic. That's what I thought it stood for. Next, we have two more currently. Please feel free to put anything else in the chat if you have any questions. This one is, how does multi-objective optimization compare to the FreeFlyer current optimizer?
So there are a couple of differences in between the single objective optimizer and the multi-objective. For starters, the single objective optimizer, typically you'll be utilizing derivatives to solve the problem, and you'll be following a path down to a particular solution. Whereas the multi-objective optimizer, it does not use derivatives, and it works in a stochastic or inherently random manner, and you're not following a path down towards a particular solution, but rather you are kind of spreading your wings and looking for solutions over here and then over here, and kind of bringing together the best of the entire solution space.
Thank you very much. And lastly, how is each transfer leg solved for in the sub problem?
So in the asteroid tour example problem, each leg of the asteroid tour is going to be solved using the single objective optimizer. So we'll start at whatever the origin is, either Earth or a particular asteroid, and then we'll end at whatever the asteroid destination is. And we'll solve a transfer that has 3 delta V's, 1 departure, 1 mid-course, 1 arrival, and we will minimize total delta V for that particular leg of the transfer in that subproblem. And then we will perform the same optimization problem again from the asteroid we just arrived at to the next location in the asteroid tour. And we'll do that 3 times total for 3 asteroids in the tour. And then we'll sum all of the delta V's for each leg, which is then the total delta V objective for the multi-objective optimizer.
Perfect. Well, that looks like that concludes the pre-submitted questions for today. If you could go to the next slide, because we don't have anything in chat right at the moment. And so now, before you go, we have a few items to cover. One, to thank Luke again for the presentation today and the discussion. in the webinar. And we have a wonderful opportunity for you all to beta test the MOO functionality for anyone that's interested. Simply drop an email to techsupport@ai-solutions.com and place MOO beta test in the subject line, and then we'll coordinate an updated FreeFlyer license for you. So take a second, you can jot that down. Next, we have 3 more announcements for you all. Excuse me. First is a reminder that both FreeFlyer Certification 1 and 2 are available. This is a great way to finish out 2024, especially with performance evaluations ending the year, or to start off the year on the right track. Simply click the QR code to take you directly to our certification page. Secondly, if you're not aware, our FreeFlyer user forum is available to connect with like-minded folks to discuss all things FreeFlyer. Please contribute to build our tribe globally around FreeFlyer. And then third, please visit our events page for our Q1 webinar, which will involve global university students sharing projects in FreeFlyer. It also shows the attendance at various conferences throughout 2025. Go ahead, Luke. Next slide. Next, again, thank you all for attending today. We greatly appreciate your participation and collaboration. As a reminder, we'll provide the recording and the slides within 24 hours to all attendees, and we'll post it to our YouTube page as well. So be sure to like and subscribe that page. If you have any questions around MOO or FreeFlyer licensing, anything of that nature, feel free to email us at sales@ai-solutions.com, visit freeflyer.com, or simply call us at the number on the screen. Again, thank you all for joining our FreeFlyer Q4 webinar today. We wish you all a very safe and happy holiday season. That concludes our webinar for today. Have a wonderful afternoon wherever you are, or evening or morning. Thanks so much for attending. Bye-bye.